Well, welcome to the 2008 Tuzo Wilson Lecture. My name is Nigel Edwards, and I am currently the J. Tuzo Wilson Professor of Geophysics. The lecture is given as a tribute to Tuzo, who is remembered as a distinguished, world-renowned geophysicist. He made seminal contributions to plate tectonics, the revolution in the earth sciences that started in the 60s. This year is a special year for us, marking the 100th anniversary of his birth. Tuzo was educated at Toronto, Cambridge, and Princeton, and returned to Toronto as Canada's first professor of geophysics. He was elected to the most prestigious scientific societies and received many accolades and prizes from his peers and laurels from his country. Personally, I always remember him as the Indiana Jones of geophysics, always talking, always traveling, always in possession of a new idea. He spent a remarkable period as Director General of the Ontario Science Centre, lifting it to one of the greatest institutions of its kind and a model for similar centres worldwide. He served as Principal of Arundel College, now the University of Toronto at Mississauga, and Chancellor of York University. Tuzo won the Vetlesen Prize and was appointed a Companion of the Order of Canada. The special and maybe the only useful role of the Wilson Professor is to persuade a distinguished speaker to give the Wilson Lecture. As an applied scientist, I elected this year to ask Professor Oxburgh, stirred by an interest of Tuzo's expressed late in his career. In an address to the Empire Club 30 years ago, he said, "There are interrelated matters I wish to discuss today. First, science and engineering are vital to our prosperity and health. Second, I wish to point out that the nature of the change that is needed to correct economic thinking. And the third is that energy is becoming scarce and expensive, and what should we do about it?" His thesis? Well, very briefly, Chapter 1, scientists like James Watt and his steam engine started the industrial capitalism. Second, economics is a subject crying out for a scientific revolution. Those of us who've lost all our money on this, well, you understand. Sustained percentage growth, as in houses, that is exponential growth, is impossible. And the final thing, the principal limitation of growth is the pending limitation in the energy supply. It is interesting that no mention was ever made of the fourth factor, global warming, which is considered so very important in present times. I'm sure our guest will have more to say on these points, and I would like to ask Professor Young, who is the Vice President of Research, to introduce our distinguished speaker to you and welcome him to the University of Toronto.
Good evening, ladies and gentlemen, and members of Tuzo's family. I'm delighted to welcome you to the University of Toronto on this wonderful occasion. And let me extend a special welcome to this year's Tuzo Wilson lecturer, Lord Ronald Oxburgh. I'm deeply honored to be introducing Lord Oxburgh. I say this as a geophysicist myself who has learned from Lord Oxburgh's brilliant work. He's quite simply one of the giants of our field. He's also a passionate and eloquent advocate for the health of our planet, and has committed much of his career to working with various groups to find ways to save the environment from the dangers that face it. Born in Liverpool, close to my own hometown, Lord Oxburgh has built a distinguished career in academia, government, industry, and excelled in each. He's a graduate of the Universities of Oxford and Princeton, and taught earth science at Oxford and Cambridge universities. At Cambridge, he was head of Department of Earth Sciences, and he was president of Queen's College. Lord Oxburgh has also been chief scientific advisor to the Ministry of Defence in the UK and rector of Imperial College London. He has also served as a consultant to the petroleum industry and to the European Commission on Geothermal Energy. He was chairman of the Interagency Committee on the Environment and Global Change, and president of the British Association for the Advancement of Science, to name just a few of the important and distinguished achievements. He's a member of the House of Lords and former chair of the House of Lords Select Committee on Science and Technology. And from 2004 to 2005, he was a non-executive chairman of Royal Dutch Shell plc. During his time at Shell, he helped to formulate the company's strategy of gaining expertise in environmentally friendly energy technologies, and he is deeply committed to corporate social responsibility when it comes to the environment. His honours are many, including Knight Commander of the Order of the British Empire, as well as Fellow of the Royal Society, the Royal Academy of Engineering, and the US Academy of Sciences, all among the most prestigious an individual can earn. And to top it all, he was for many years, and maybe still is, a marathon runner. Lord Oxburgh's achievements are significant by any standard, and he is one of the world's amazing and great citizens. So again, ladies and gentlemen, on behalf of the University of Toronto, I'm very honoured to introduce Lord Ronald Oxburgh speaking tonight on all our energy futures.
Well, ladies and gentlemen, I have to switch this on or you won't hear me. But first of all, may I express my gratitude to the university at inviting me to speak on this occasion. It's a great honour to be invited to give the Tuzo Wilson lecture. And I will also like to thank the department for the hospitality they've shown me yesterday and today. I've learned a great deal, and what more can you ask? I'm going to talk today cover really a very wide canvas. And please forgive me, but some of it I'm going to have to do really rather superficially. But I want to start by showing an idiotically simple diagram. Ultimately, it's about people. And I'm going to be talking about energy, and that's going to be my focus today. But what we have to remember is that we actually live not only in a crowded Earth, but in a very complicated Earth, in which water is at least as important as energy, and biomass, anything that we grow, is important as well. And these three important elements in our existence interact with each other. You can't grow things, you can't have biomass, you can't have plants, you can't have animals, unless you have water. Energy and water, closely related. You can't run a power station unless you have water to cool it. And there are a whole range of other interactions as well. In order to grow biomass, in order to grow things, you use energy. There is a continuous interplay between these three. And then, lurking in the background, you have climate. And climate, of course, affects the water and affects the biomass critically. And then, of course, we have the elephant in the background, which is the interaction of energy with climate. So what I want to emphasize is that though I'm primarily talking about energy, we must never forget that this is part of a large and complicated system. Now, the 21st century, on which we've recently embarked, is going to be different from earlier centuries in a whole range of different ways. Now, I guess every century is a bit different from its predecessors. But first of all, there is now a widespread recognition that burning the fossil fuels, on which really the industrial advances of the 20th century were based, is actually damaging our climate and our environment in the broadest sense. But secondly, we find ourselves in a situation in which we have a near total dependence on fossil fuels. It's not very comfortable. And at the same time, the world population is mushrooming. Over the next 50 years, the world population will probably grow to about 9 billion. And those people are actually going to become progressively more prosperous. Doesn't mean that everyone will be prosperous, but it means everyone will move up a little bit. And as people become more prosperous, they have an increased energy demand. And indeed, world demand for energy today is increasing far beyond the expectations of the professional bodies, even 10 years ago. And then politics has come into energy in a way that wasn't really expected. We find that, and I'm going to talk a little bit more about this in a minute, but we find that various regimes that actually have energy resources are using them as political levers. And furthermore, I will argue, and I'll show you the reasons in a minute or two, that we are at the end of the era of cheap fossil fuel. And there are good reasons for that, but it does mean that the resource, fossil fuel, is now achieving a scarcity value, and this means that there is an enormous shift in world purchasing power. And the wealthy countries now are those that have fossil fuel resources, and at very high prices, they are sucking in wealth from particularly the developed world. And that is why world leaders are now heading towards the Gulf to borrow their way out of the current financial crisis. Now, let's just look at these couple of these aspects in a little bit more detail. The recognition of the role of fossil fuels in climate change. Now, in a sense, this could be regarded as very boring because everyone knows about this. But still, I suspect in this country, just as in North America and in parts of Europe, there are still some people who are not really quite sure about climate change. They say, well, hasn't the world's climate always changed? Isn't that what geology is about? Well, of course, that's absolutely true. But I think that in an effort to make the point about climate change in a way that people could understand, people have actually tended to use the wrong evidence. And as far as I am concerned, let me go back. They've tended to use, and I need to go to here and show this picture. Now, this plotted vertically is the carbon dioxide content of the atmosphere, and plotted horizontally is time, going back to 60,000 years, and there is today. And what you see is that during the last ice age, this is the time, you can see that carbon dioxide in the atmosphere went up and down. Round about 18,000 years ago, there's 20, we came out of the last ice age, up this, right? And it ended roughly 10,000 years ago, and then we went into a gently warming period. Until 150 years ago, when suddenly the CO2 concentration in the atmosphere went through the roof. And in 2004, it was 379 parts per million. Now, this is, I think, extremely important. The first thing is, that is our spike. That is the size matches the CO2 output from the fossil fuel that we've burned. We know roughly how much oil, how much coal, and so on we've burnt in the last 150 years. And the spike is the right size, because round about half of this goes into solution, dissolves in the oceans. Furthermore, the chemical fingerprint of the CO2 in the atmosphere tells us that there is a significant component that actually came from fossil fuels. Furthermore, there isn't really any geological parallel of anything quite like this. If you go far enough back, I mean a number of tens of millions of years, you can actually find a peak as high as that, but you cannot find anything as steep. That is effectively, from a geological point of view, an instantaneous injection of CO2 into the atmosphere, and really the only thing you can think of that can do it is our suddenly starting to burn coal and then oil. And then finally, from very simple physics that was really first recognized in the 19th century by the Nobel Prize-winning chemist Arrhenius, he pointed out that actually burning coal would increase the world's temperature, the globe's temperature, and because he had lived in Scandinavia and found the climate a little bit too damp and cool for his liking, he actually thought that this would be a very good thing. So he predicted global warming, and indeed roughly the right scale that we're seeing it on that long ago. So this is what is unique about the present situation. It isn't stranded polar bears, it isn't early springs. All of those things are, if you like, are consistent with this, but this is what is unique about today, and it's very important to remember that. Well, let's go back to the main story and talk a little bit about security of supply. Well, whether you look at Mr. Putin or whether you look at Venezuela, what Mr. Chavez have done, you get the same message. Indeed, energy is now a political tool. And I actually rather like this one from Le Monde, and I added that little bit, and I do control 70% of the world's gas. Clearly, the use of energy supply as a political weapon is here to stay. Now, the final point that I want to make in this introduction is that we really now are at the end of cheap energy. And so it's perhaps worth saying a little bit about the oil price. And until very recently, oil was largely sold at the cost of what it was getting, cost of getting it out of the ground, plus a margin, plus taxes and things like that. But it was simply a resource that you continued to dig out and then sold in a highly competitive market. But now, and I say now, it's not really true today, but it was true 6 months ago, world demand was rising significantly faster than supply. And those two curves were joggling along together, leading to great concern about the future. Now, the fact that we are entering a world recession means that we're in fact going to get a couple of years respite. But believe me, this respite is temporary. And there is really little chance of a significant long-term production increase. It can go up a bit, there can be new discoveries, but fundamentally, oil is a finite resource. And it isn't that there is a shortage of oil, it's a shortage of easy oil. We've probably got most of the easy oil. And you've got to remember that when a company goes into an oil field and starts pumping, they probably leave 65 or 70% of the oil in the ground simply because it was not worth getting it out at what they perceived to be the likely price of oil during the life of that field. So it's not a shortage of oil, but it's a shortage of cheap and easy oil, and that is what we are facing. And as I say, historically, it was really largely priced at. Now it's actually acquiring a scarcity value as well. The other big difference is that today, governments, not international oil companies, are calling the shots. Governments, one way or another, control between 80 and 90% of the world's oil and gas resources. And that is another way. This makes it very easy for them to use it as a political lever if they want. But there is another element as well, and this is a new element, and it's summarized in this statement by King Abdullah of Saudi Arabia. It didn't get much attention at the time, but it was a comment made earlier this year. I keep it as no secret that when I'm told about new finds, I say, leave them in the ground, children need it. And really what he's saying is what dawns eventually on any country, that indeed has mineable and exhaustible resources. And this indeed applies to Canada as well. That actually your strategy, and this is what King Abdullah is saying, his strategy is to husband those resources and then sell them slowly at as high a price as they can. And that indeed is what Abdullah is saying. And I think there is every indication that OPEC is now likely to defend $100 a barrel. Before the present recession set in because of the collapse of the global banking system, it was clear to OPEC that the world economy did not collapse at $100 oil. The Middle Eastern countries, the OPEC countries, have really no other resource. They have major spending commitments because they were expecting this price to continue. They are going to defend $100 if they possibly can, and they have to balance tread a very fine line between pushing the price as high as they can, but at the same time not making the recession worse. But believe me, $100 is actually what they're aiming for. And the other point, of course, is that the alternative sources of oil, which I'll be talking about shortly, are cost, roundabout in the region of $80 to $100 a barrel. So the final point is the one with which I started, and that is that there is a global shift to expensive energy. And in the 21st century, energy is going to cost somewhere between 3 and 6 times as much as it did in the 20th. So it is goodbye to the century of cheap energy, and we're going to have to re-optimize our systems in all sorts of ways. Having energy expensive means that all sorts of things which we've regarded as cheap and easy become expensive. We're not necessarily going to live worse, but we're certainly going to live differently. So the dilemma that we have, we've got to reduce our dependence on fossil fuels for the reasons that we've already discussed. And furthermore, there is no real possibility of a rapid reduction in fossil fuel use because our infrastructure changes so slowly. We can say using fossil fuels is a bad thing, but we don't really have alternatives, and all our power stations, all our infrastructure is geared to their use. And so we've got to recognize that this is an important change, but it's going to be slow, and this actually means that we have to start now, because there are very few immediate alternatives. But we have to develop alternative energy systems, and particularly different patterns of use as quickly as possible. And by different patterns of use, I mean we have to be careful not to waste energy. We have to think of ways of doing traditional things in ways that use less energy than we have traditionally done in the past. And finally, we have to try to mitigate the effects of fossil fuels, FF is fossil fuels, by capturing and in some way tying down or immobilizing the greenhouse gases while we look for alternatives. Now, let's look at the situation today. This really gives you a feeling for the relative contributions of coal and oil and gas. And these numbers are gigatons of CO2. 2004, the proportions haven't changed very much. But you see, it's nearly all coal and oil. And coal is mostly power generation, oil is mostly transport, and gas was predominantly heating and power generation. Now, what we have to recognize is, although we lump things together and simply talk about energy, the requirements of transport are very different from those of power generation. Because in transport, you've got to have a fuel which has a very high energy density. Ideally, that doesn't weigh very much, that doesn't take up much space, but packs a great deal of energy into a small space and a small mass. For power and heat generation, that doesn't matter nearly as much. So we have very, very different requirements. So let's talk first about travel. And today, we're more or less totally dependent on the internal combustion engine. And I use the acronym ICE, the ICE, the internal combustion engine. And you can't use an internal combustion engine without liquid fuels. So this means that until we find an alternative to the internal combustion engine for general application, we are tied one way or another to liquid fuels. And that's pretty awkward. Now, traditionally, that's been mineral oil, which we've all agreed, I hope, is both a diminishing resource and it's environmentally damaging. So we need to look for alternatives to the internal combustion engine, and we look to alternatives from mineral oil. And one of the slightly unfortunate things is that you can make a very nice fuel either from coal or from gas. You gasify the coal, you produce something called syngas, and you can make a nice clean fuel. The trouble is that it is a really dirty process, very carbon intensive indeed. And although that is certainly going to be done by some countries in order to reduce their dependence on imported petroleum, unless you do something about the emissions associated with the process, it's going to be a real problem. But you can also make good fuels from biomass, from things which are grown, more or less anything grown, and indeed from organic wastes. And these represent a real opportunity for clean fuels. So let's talk a little bit now about biofuels. Now, biofuels really are any fuel, a fuel that you can make from anything that is grown. You can make them from crops or from wild plants, or you can use agricultural byproducts, or you can use the organics from urban garbage and wastes. And I'm going to show you an example, I'm going to talk a little bit about this. I'm not going to talk about the urban garbage, and I'll simply say now that the one thing that the developed world is really good at is making garbage. I mean, we produce it in prodigious quantities. And roughly 50% of urban garbage is organic material. And anything that is organic can be gasified, and you can make a good fuel from it. It may not be the best use, but you can do it. Now, if when you do any of these things, they've got to make sense financially, and you've actually got to make sure that it has a sensible carbon balance and energy balance, and that you're not doing other environmental damage in the way. Now, broadly speaking, you've got three sorts of product. You've got ethanol, which you can produce from fermentation of sugars, and ethanol will mix with gasoline, and indeed you can tune engines so that they will run on virtually 100% ethanol. Biodiesel, which the traditional way is to make it from vegetable oils, from oily seeds, which you crush, but you can also make it from recycled oils, which have been used for other purposes. And you can make synthetic fuels by gasification, and you can end up with either diesel or gasoline or aviation fuel, depending on what you want. So, first of all, let us talk a little bit about, if you like, the old and, dare I say, bad way of making ethanol. But this is what has been done very recently, is still being done in the United States, and has led to quite a lot of difficulties and corn shortages for food. And let me say right at the beginning that I think using food for making vehicle fuel in a world which has a rapidly increasing population that will need feeding doesn't look to me like a winning strategy. But one of the things that I emphasize is that whatever you do, you've got to make sense from an energy balance point of view. There's no point in spending a lot of energy or putting a lot of CO2 in the atmosphere if, in fact, you're not saving anything. So let's see what's involved in producing ethanol from corn. Well, you've got to cultivate the field. It costs you that much energy, and energy units plotted vertically. You've got to put fertilizer in. Fertilizer very strongly dependent on fossil fuels. You've got to harvest. You've got to process. And that is the total energy of the fuel, of the biofuel that you've made. And you see that you've actually gained very little. And you only have to be a little bit less efficient in one of these steps. In fact, for it to cost you more energy to make the fuel than you get out of it. And this is only done in the United States because of the perverse incentives offered by agricultural subsidies and the very strong farming lobby. Now, that's not the end of the corn story. If you look at what's left in the field, the corn stubble, you can be clever with that, and you can make a very good fuel out of that. And so I'm simply going to show you, for comparison now, a cellulose ethanol, which is actually made from the straw, or part of the straw, that is left in the field, or is a waste product, after you've actually taken the showy part of the corn, which is what people eat. And I'm going to show you a little bit about the process here now. This process was really first developed in a commercial or semi-commercial way by a small Canadian firm called Iogen, who operate out of a little pilot plant on just outside the perimeter fence of Ottawa Airport. And basically what they did was start with corn stubble like this, and then they developed from various fungi enzymes that would break the cellulose in the corn stubble down into its constituent sugars, and then they fermented these just as you would any sugar in order to make ethanol. And this last bit shows the first consignment on April 2004 being waved off by your Prime Minister of the time and the CEO of the company. And indeed, at that time, and maybe today, as far as I know, government vehicles in Ottawa were actually fueled by ethanol produced this way. So this so-called second generation biofuel, which actually uses what was at the time regarded as an agricultural waste, is really, I think, a very important signpost for the future. The one thing you shouldn't ask me is what that ethanol costs. It's a lot. And all of the research effort today goes into finding cheaper ways of actually getting the right drugs to break down the straw and to give you something much more cheaply than, in fact, that ethanol that we're seeing there. So that is a very important way forward, and certainly the US is committed to developing this technology over the next 5 years or so. And that indeed was a collaborative initiative between Iogen and Shell. Another way of doing this or producing a biofuel, is to take a plant which will grow on land which is no good for agriculture and which doesn't mind fairly tough conditions, which is drought resistant, but produces oily seeds. And one of perhaps the best prospect here is something with a funny name, Jatropha curcas, normally described as Jatropha, requires a lot of labor, but it grows in tropical countries on marginal land where by and large the people have enormous difficulty scraping a living. And these pictures that I'm going to show you now are from Swaziland, where the people are very poor and welcome the opportunity. Jatropha oil is not really edible. It's was used by Portuguese missionaries for its pharmacological properties. It's a diuretic, and there is a reasonable yield from wild trees, but it's never really been a cultivated crop in the past. You can use the crude oil directly in static engines, but you have to refine it if you want to use it in your BMW. And the provisional estimate that we can get is that there's something like a 60% saving of emissions over mineral oil. Now you just see some pictures. These are the seeds. You saw this in the previous slide. Sorry, you saw the seeds being planted. There are the seedlings coming up. There they are planted out, and there you've got young Jatropha plants, probably about 4 months old. And what you can see is that this is rough land, but you've got, in fact, okra planted in between. because okra will grow in the shade of the Jatropha. And then when they get a little bit bigger, that's the size of a Jatropha bush. Generally, the idea is, although these will grow into trees 4 or 5 meters high, they're not very convenient for actually picking off the fruit, and so they're pruned down to that sort of size, and that is what the seeds look like. Those are the fruit, and there are the seeds which you crush to get the oil. And there are probably several other non-edible things that you can grow of this kind, which will grow on marginal land, which don't compete with food, but which can give us fuel. Now, there are other ways that you can make liquid fuels as well, but I've just given you a couple of examples. The final message is that there are biofuels and biofuels. And if you look at the amount of CO2 per unit energy, you can see that you've got low sulfur diesel, you've got unleaded petrol or gasoline here, and then you have ethanol from the US corn. And as you come down here to the ethanol produced by Iogen from corn straw, you can see that you in fact have an enormous advantage over the unleaded petrol or the mineral oils on the other side. And the trick is actually produce biofuels as close to this ethanol from wheat, ethanol from straw, as you possibly can. And this is certainly going to be done. And this is one of the ways that we shall keep ourselves in liquid fuels. And let me point out that although in a minute or two I shall show you that there are alternatives to the automobile, for automobile propulsion, for aircraft, there isn't really any good alternative on the horizon. And it's quite likely that we shall go on, but even 50 years from now, we shall be using biofuels actually to fly aircraft and to fuel the internal combustion engines of aircraft. Now, who can tell what technology is going to develop over that time, but that's the way it looks at the moment. Well, I said I'd say a word or two about road vehicles. The typical internal combustion engine in a car is not really a great device. It has an efficiency of around 20%, which means that, you know, of the intrinsic energy and the fuel that you put in the tank, 20% or less goes into propelling the vehicle. And why is that? Well, you have losses on idling, you have losses on braking and transmission, and, you know, every car has got this splendid device built into it to throw away energy. It's called a radiator. I mean, simply, there is excess heat generated by the internal combustion engine, which is thrown away. And that's why the overall efficiency is so low. Now, if you go to electrical drive, you can actually get rid of some of those and possibly all of them. The question is, if you go to electrical drive, where do you get your power from? Do you get it from a battery, or do you get it from a fuel cell? And let's look at the battery route first. And of course, we all know about the hybrid. The Toyota and Honda, I think, were the first in the field with hybrids, where you have a battery which is topped up from a small internal combustion engine, which occasionally helps on propulsion. And in certain applications, particularly around town, you can get much better mileage, much more efficient use of your fuel than you do from a conventional vehicle. Once you get out to running at constant speed on the highway, the difference is actually much less, because obviously you don't idle, you don't brake, and so on. Now, the things are changing, however, and the battery technology is improving fast. And the next stage after the hybrid is, in fact, to go to full electrical propulsion, so that you don't have an internal combustion engine in the vehicle at all. And you can do this with in various ways. You can have an overnight charge battery. You can have modular battery exchange in which, depending on the size of the car, you have a different number of battery units. But the point is, instead of going to a gas station to top up with gasoline, you simply change your battery. That is the other approach. And in fact, there are companies that have developed an automatic technology for this. It isn't a matter of going in with wrenches and taking the leads off. You simply drive up to a bay, go and have a cup of coffee, and by the time you come back, the battery is changed by elves or the like. The final alternative is a quick recharge. And there is now a battery available which, with a lot of power, which gives you 80% recharge in 10 minutes. And that is really an important change of technology. So let's look at how the alternatives, and I'll show you some pictures of these in a minute. The alternative is to go to a fuel cell and effectively operate on hydrogen. I am not enthusiastic about this. I know Arnold Schwarzenegger has talked of his hydrogen highway and the like, but I don't think that this is the way forward. There really isn't any efficient way of making hydrogen at present which doesn't depend on fossil fuels. As is rumored, transgenic bugs can be bred which will actually produce hydrogen from seawater. That could change the situation profoundly. But without something like that, I don't really think that this is on. Even if that does happen, you need a very profound change in infrastructure in order to bring hydrogen in, whereas the change to an electrical car can be done much more gradually. So I think the other thing that you need to do is to reduce the weight of vehicles. And if a lot of emphasis goes on this, as indeed has happened in the Boeing, the Dreamliner, which is a little bit delayed, but a lot of that has very advanced materials in it, which cuts the weight of the aircraft significantly. If you can reduce the weight of vehicles, again, you can manage with a smaller motor, you can manage with smaller amounts of fuel, and you significantly improve the fuel economy performance. Well, let's look at some of the electrical vehicles. That was, I think, the first. This is the Tesla, the all-electric car. It's produced in California. It has performance to make Ferrari concerned, 0 to 60 miles an hour in 4 seconds, really exploiting the massive torque that you get from electrical motors, and a 250-mile range. The British parallel to that is the Lightning, which is based on an Aston Martin, the James Bond car. Now, that uses the advanced battery that I talked about a moment ago, and is capable of 80% recharge in 10 minutes and has the same sort of range and performance. But I personally don't think the fast recharge batteries are necessarily going to be the way of the future. If you just think about it and you think of the size of the leads that you are going to need to get that number of amps into a vehicle battery in 10 minutes. I mean, you're thinking of something about this, the diameter of your wrist. And I think that this is not very likely, and I suspect the other alternatives are going to be the way forward. Then, of course, you have the Zen, the Canadian vehicle, which I understand is having real problems with the licensing authorities here, who don't think it's a serious vehicle and oughtn't to go on the roads. Fortunately, that is not the fate of the Think car, which is produced in Norway. And I actually, about 3 weeks ago, I got the opportunity to drive one of those. It charges overnight with one battery, or in 3 hours if you buy a more expensive battery. You can see it's got a range of 170 to 200 kilometers. And it's a fun car to drive. It's about the size of a VW Bug, and it's got tremendous acceleration, good road holding, and I think that these are certainly going to take off in Europe, but certainly we don't have the regulatory problems that you appear to have here. Okay, now there are upsides and downsides of electrical propulsion. You've got 0 local emissions, so you don't get a smoky city. And of course, if you go to full electrical propulsion, you massively reduce the number of moving parts, which really means that maintenance is significantly reduced. And manufacturers are talking of maintenance-free vehicles. Don't you believe it? But it's certainly going to be better than with conventional cars. But you are going to get round about 80% energy conversion efficiency in the car, but what about the efficiency of the power station, which generated the electricity in the first place? Well, power stations vary depending on their age. Most power stations in the West deliver at least a 30% efficiency, and modern ones will give you 50% from fossil fuel. So even if you've only got 30%, you're actually seeing something like a 24% efficiency overall, which is better than the 20% you got simply burning the gasoline. So you shouldn't bother too much. But what we're seeing here is, I think, a move towards an electrification of the economy. And I think we're going to see this progressively over the coming decades. More and more done by electricity. And how you generate the electricity we'll talk about in a minute or two. But even if you use fossil fuels, you want to burn them in a limited number of places where you're prepared to put in the technology to manage the emissions. Okay, so let's talk about generating electricity now. We've talked about transport, now let's talk about power generation. Now, the clean menu looks something like this. We've got nuclear fission. At the moment, if you like, that is a fairly mature technology. I mean, people can feel very emotionally divided about it, but it is a pretty mature technology. We have the traditional so-called continuous renewables, hydroelectricity, and geothermal. Fine where you can get them, but many parts of the world simply don't have either of those natural resources. And then you have the discontinuous renewables, the intermittent ones. Wind, waves, tides, solar. All great when they're available, but they're not available all the time. Then we've got transitional use of fossil fuels, but you trap the emission. You do something with them so that they don't pollute the atmosphere, and maybe sometime in the future we see nuclear fusion. I was a student, it was said to be 60 years away. Well, people are now saying 30 years away. And certainly there have been some major advances, as people here know. I think the main problem that they face at the moment, or probably the largest thing, is getting materials from which you can build a power station. In principle, you could build a power station at the moment based on fusion, but it would have a life of about half an hour, and that isn't really long enough. Now, the thing is that the real game-changing technology for the discontinuous renewables is if you could store the energy that they generate. And I'm going to underline that as one of the really pivotal technologies that we have to develop. Because an intermittent source plus energy storage looks like a power station. And in other words, you have energy when you want it. Now, there are various technologies that have been spoken of to store energy. You can actually pump water uphill to a reservoir so that you can have hydroelectricity when you want it. Good, but limited availability. People have used flywheels. People have tried fancy batteries. Or you can use hydrogen. Again, most of these are pretty inefficient. What I'm going to talk a little bit now, and I'm talking about this today partly because it's a Canadian initiative, and I actually think it's very important, is a battery initiative. And this is a diagram from the website of VRB Systems, who are a Vancouver-based company. They took the intellectual property, they bought the intellectual property of a British company called Regensis, which went bust when the government withdrew its support at just the wrong time, and then they improved the technology significantly. But fundamentally, this is a battery, and it's based on a regenerative fuel cell and 2 massive vats of electrolyte. And the electrolytes are solutions of vanadium salts, and as some of you will know, vanadium has 5 valence states, and fundamentally what happens when you pump energy into this, you pump electrons one way, and you change the valence state of the salts, and when you pump it out, you just reverse the process. Now the beauty of this is that you can scale it up as much as you want. And it has something like an 80% efficiency. You get back around 80% of what you put into it. Could talk about this at greater length, but I'm not. The other actually very good aspect of it is that it has a very quick response time, measured in milliseconds. So it's ideal for backing up. And Ireland is actually planning to take half of its base load from wind generation, backed up by flow batteries supplied by VRB. And that is what one of these massive batteries look like. It looks very agricultural, and indeed it is. And these are the big vats of electrolyte. Effectively, it's maintenance-free, and they've got a number of these operating in different parts of the world. They're largely used actually as backup batteries for telecommunication systems, where the fast response time is much appreciated. But as I say, the Irish situation looks like the first time that they will be deployed in anger on a big scale. So this is one of many possible ways of storing energy, but this is one of the really big challenges. So let me shift now to fossil fuels, on which we're going to depend, whether we like it or not, for decades. Now, it's quite instructive to look at the distribution of fossil fuels around the world. And on the plot, I'm sorry, the scale is missing its units. But what's plotted vertically is reserves of oil and gas. And you can see that we've got various countries plotted horizontally. And on the left, you have the big energy exporters, and on the right, you have the big energy importers. Now, there are many more that you could put on either side. But you can see that on the right, we've got the 3 most energy-hungry economies of the world: the US, China, and India. And the normal people are here on the left. Lots of oil, lots of gas, and so on in the Middle East. And I'm ignoring, for the purpose of this slide, various kinds of unconventional resource. But look how the situation changes if we add coal to that. And you can see the whole situation is transformed. Over on the right there, you have something like 2/3 of the world's known coal reserves. And that coal on the right is going to be burnt whether we like it or not. The US is going to burn coal for reasons of energy security. China and India are going to burn their coal because they're poor countries, and as you saw a moment ago, they haven't got much else. We would do the same in their situation. So what are the implications of this? Well, the emissions that you make when you generate power at a power station depend on 2 things. They depend on the fuel that you use, and they depend on the technology that you use for burning that fuel. So over on the left, you have hard coal burnt in, if you like, what is an old-fashioned power station, and plotted vertically here is CO2 per unit energy produced. And you can see hard coal has a high CO2 cost. Oil is pretty bad as well. If you go to a more advanced coal power station, you can do a little bit better. Gas is better in an old-fashioned power station. Better is still if you go to a more advanced one. And you can see over here on the right, with a very low carbon footprint, is hydro and nuclear. But if you can trap the emissions, the CO2, the greenhouse gases, in from a coal-fired power station, you can actually bring coal down from that to that. And that is a prize worth going for. And this is what is meant by carbon capture and storage. And the ideas involved in carbon capture and storage are summarized in this cartoon. The idea is that you have a power station here, which you hope is conveniently close to a coal mine so that you don't spend vast amounts of energy trucking the coal or taking it by rail to the power station. From the power station, the electricity goes off down the wires. Ideally, the only thing that goes off into the atmosphere is water vapor and nitrogen, things like that. Your CO2 has been separated and then is pumped along a pipeline, and in this cartoon is put somewhere underground, perhaps into an abandoned gas field, and you know that it's tight because it was able to hold gas for many millions of years, or perhaps an abandoned oil field. But the present concept is that most CO2 trapped in this way will be put underground. This is what's meant by carbon capture and storage. So why don't we do it everywhere? Well, there are one or two problems. I mean, the first is that the carbon CCS, carbon capture and storage, the technology is still immature. Everyone knows that we can do it. All of the bits have been demonstrated, and it can be done. But it's still really pretty much brute force. It's slow to implement, and it involves heavy engineering. And in heavy engineering, there's a great deal of learning by doing. And the fact is, because these things take time to build and develop, if we want to start reducing emissions from coal-fired power stations within the next decade, we have to begin today. And governments are probably just beginning to wake up to that. And for reasons that I'll show you in a moment, it's exceedingly important that the technology be developed to retrofit power stations. Power stations have lives of a minimum of 30 years and up to 50. So there are a lot of power stations that are being built today that are going to be built with us, till 2060. So if we want to tackle the problem of their emissions, the technology has to be retrofittable. And this means that, and the current technology basically is not very good for that, because it takes a great deal of space, big footprint, and there isn't always room to do it. And apart from that, it is expensive. And using the technology as we see it today, it looks like a 30% increase in the cost of electricity. And that is a pretty rough estimate. I don't think the cost increase will be less than 25, and it might be as high as 50%. It's quite a penalty, and we can talk about why that is afterwards, if you like. Now, I don't think that this is the technology with which we are going to go forward. Got to see a spelling mistake there. You never see these things when you're putting it all together. I don't think this is the technology that we are going to be using in 10 years' time. I think there are important alternatives which are being worked on. And further beyond that, there is now discussion of technology for pulling CO2 out of the atmosphere directly. Now, this would be a real game changer if it happened. It must be cost and energy effective, and frankly, it looks implausible. But a number of credible research groups, one in chemistry at the University of Alberta, another at MIT, believe that they can do it. And if they can, it would be fantastic. But pulling something out of the atmosphere, which is only present at the level of a few hundreds of parts per million, does not look like a winner. But if they can do it, it would have enormous implications. And it would mean then that it didn't matter where in the world you trapped the CO2, and you could trap it exactly at the places that you wanted to manage it, to put it underground, or to use other technologies to immobilize it. So it could be incredibly important, but we've really got to see it demonstrated. And there are also possibilities of geoengineering. Now, let me show you why this technology is important. And I'm going to take now an example from China, not because of anything special, partly because the data are available for China, and China is big, but you could do the same with India or other developing countries. Now, this diagram is a bit unusual, so it's worth taking a moment or two to understand it. Plotted vertically is amount of energy consumed per capita per year. So it's the individual energy use, the total amount of energy used by an individual. Plotted horizontally are numbers of people. And these points here show per capita energy use and population size from 1965 onwards for China up to the present day, which is somewhere about here. And you can see that as the population grew very rapidly, that is 1 billion, as it grew to 1.3 billion here, suddenly things changed and China began to become very prosperous, and of course energy use began to increase. Now, China today is about there. The developed countries are today about there, with something like 5 times the per capita energy use of China. Now, the interesting thing about this diagram is that if you multiply a number of people by a per capita energy use, you come up with a rectangle like that, which corresponds to the amount of energy that they've used, and because the energy is largely produced by fossil fuels, that is a proxy for their emissions. Now, if we do the same for China today, that is what we see. And if you think of that rectangle there, transposed, say, to there, you can see that Chinese current emissions are about half of those of the developed countries, which is about right because, as you know, the US is responsible for about half of the emissions of the developed countries, and this year Chinese emissions and US emissions are about the same. But if we look going forward, what happens, and China is commissioning coal-fired power stations very fast. Their highest priority, perfectly understandably, is to get power to a large number of people in central and western China that do not have mains electricity. If we look at current plans, not going very far forward, that is what happens. And that is largely based on coal-fired power stations. And that is why it is extremely important for the world that we develop the technology which can be retrofitted to those and power stations in our countries, India and other places as well, to trap those emissions. Now, if we take a quick view forward of 2050 from today, I think we will see a world in which we are dependent on agriculture and mariculture, things we can grow on land, things we can grow in the sea. Because our fossil resources will become very precious indeed. They will provide food for humans and animals, and they will provide the feedstock molecules for actually pharmaceuticals, plastics, and a whole range of things that we don't think of as derived from coal and oil, but they certainly are. These we are will have to come from things that we grow. They will also provide energy liquids, as I've already spoken of, for the internal combustion engine, as long as we need it. And for power, I'm sure we are going to be using wind, wave, sun, energy, nuclear, and perhaps things that we don't know about. But we are going to have to move off fossil fuels towards something that looks like that. Now, what about the present financial crisis? I couldn't conclude without saying something about it. Certainly going to reduce economic activity to a significant extent. And it will certainly slow the growth in emissions, which is a good thing. It will give slightly more time for thought and for planning, and it will give technology another couple of years to catch up, which is also a good thing. But it will not reduce the urgency for action, because we are in a race against time. I mean, I've not given one of those lectures today in which we recite the catastrophes that are going to befall us all if we continue to pump CO2 into the atmosphere. That doesn't mean I don't believe them. I think they are right, but this is not what this lecture is about. There is urgency to do something about this. So, what are my conclusions? In this sort of superficial skating over the area, I think you can see that the challenges for the 21st century are large, but they are manageable. And I think that is the thing to bear in mind. Life is going to be different, but it's not necessarily going to be worse. It is the end of cheap energy, and there is no universal solution to energy use. We have to adapt. And the renewables that are available in one country will be different from those that are used somewhere else, because their distribution is not uniform. There are places where it makes sense to use solar, particularly in the Mediterranean regions. The higher the latitude you go, the lower the importance of solar, unless we actually make prodigious breakthroughs in energy storage. It is going to be essential to manage the greenhouse gas emissions from fossil fuels as long as we use them. And that is why carbon capture and storage is important, as I just showed you a moment ago. And the two key technologies, as I emphasized, are energy storage and carbon capture and storage. If we can crack those two in a big way, many of the other problems will fall away. Equally, it's going to be coming up with a sensible solution which manages this global problem will depend on the developing countries collaborating and working in a sensitive, sympathetic and realistic way with developing countries. Because, developing countries look at this problem and they say, yeah, we understand about the greenhouse gas up there. Wonder how it got there. Didn't you people have an industrial revolution 150 years ago? That's your problem. You got us into this mess. You fix it. Now, no one is quite as rude as that, but that is what they think. So we are going to have to help develop this technology and certainly help pay for its deployment. And finally, I hope I've left you with a feeling of urgency. Thank you very much. I'll repeat the question because people at the back might not have been able to hear it. It's about the oil sands, the tar sands in Alberta, and the point was made that you use a significant amount of energy, possibly more energy, to actually get the stuff out than you actually get from it. There are two sides to this. There is, first of all, the energy balance, and there is the environmental impact. I've actually been to Athabasca and talked to the people there and seen what's been going on. I think the environmental impact can be managed and is being managed. Whether it's as good as it should be is a separate question. But when you talk to the Cree people who are there, what I was told by tribal chiefs is until this happened, our communities were going to hell in a basket fast. He said the environmentalists would not let us sell our furs, and we only got two things here. We've got fish and we've got fur. And he said these communities were dying. The young people who had something about them actually went south and left the community. Those that stayed here spent their time high on drugs. Now you've got a thriving industry with local people doing things. So in a sense, the environmental and social side is not all negative. In terms of the energy balance, yeah, you're quite right. I think there are two really bad things. First of all, you do lose a lot of energy. I don't actually think that you come out negative, but you get quite close to it. The other side, of course, is that the process is a filthy one, producing a lot of CO2. Now, if companies that are doing this develop and implement carbon capture and storage, that is the first requirement that I would put on them to continue doing this. The second thing is that it really has to do with the form of the energy you want. I pointed out that your requirements for static generation of power are different from those for producing liquids. And what the oil tar sands do is actually produce liquids on which you can reuse vehicles. And so, for example, if you were to say, right, what we're going to do is build a nuclear power station, which would obviously upset some people up here, and use nuclear power for producing liquids because we want to drive vehicles, there would be an argument. But I find it all pretty difficult, but I think you can just about get round it as some sort of transitional phase, but I don't much like it. Yeah, here it is.
Can you talk about carbon trading and is cap and trade, is that the best way of cutting carbon emissions?
Okay, the question was, what about cap and trade? And is this a sensible way of managing carbon emissions? I mean, for people who don't know, cap and trade is the system which has been introduced in Europe a couple of years back, by which initially a limited number of large emitters of CO2, particularly power stations and things of that kind, were given a number of allowances for emitting CO2. And if they exceeded their allowance, they had to buy an allowance from someone else, and so allowances achieved a value. And if they were able to improve the efficiency of their operations and not use all their allowances, they were able to sell them. Now, over the first few years, this had virtually no effect on emissions within Europe, and it has been widely criticized for that reason. I actually think it was fairly smart, because if you're introducing a fairly novel system of this kind, you've actually got to get the bugs out of it first. What is going to happen in 2012 is that the number of allowances is going to be very severely restricted. And first of all, and secondly, not only are they restricted, but half of them are actually going to be auctioned. So the price of carbon is actually going to go up significantly. And this means that the incentive for people who have power stations or other businesses which emit lots of CO2, the incentive to do something about it is actually significantly increased. Now, the real question, I think, is whether the price of carbon is going to rise high enough to actually be a really powerful incentive for people to do carbon capture and storage. And the price that people are talking about for carbon capture and storage is probably something like $60 a ton, $70 a ton for CO2. And at present, the price is about half that, something of that order. So it certainly is a way of achieving what you want without putting money into the government's pocket. And from the industrial point of view, this is seen as a preferable alternative to simply putting a tax on CO2, because what you're trying to do is restrict the amount of CO2 in the atmosphere, so that is the limit which you impose with your carbon allocation. So the answer is maybe.
Can you comment on Boone Pickens' program? And I think he advocates natural gas-powered cars.
Yeah.
Can you comment on that?
Yes, natural gas powered cars are significantly better than conventional gasoline cars. The emissions per kilometre driven are something like half those of conventional cars, but they will not be as good as electric cars.
Right. Okay. Thank you.
Yeah, over there.
I'd like to make a comment to something which you have not mentioned yet, and that is savings.
I mentioned it in passing when I said we've got to change our way of life.
About 15 years ago, they created a think tank at ETH in Zurich.
Yeah.
And they created the 2000 Watt Society.
Yeah.
That means they're very interested in getting the energy consumption down to 2 kilowatts per person.
Yeah.
And I think about 5 years ago, they said it was possible to get to 3.5 to 4 kilowatts with presently known technologies. And the most expensive part was the insulation of houses. So that was a very interesting part.
No, the question was, what about energy saving? And I didn't emphasize that at all, but I hope that I had indicated that by changing our way of life, I meant, yes, and the speaker referred to a symposium that was held at ETH in Zurich a couple of years ago, where they were talking about getting the cost of, or the personal energy expenditure down to reasonable levels, and the conclusion was raised that the cost of insulating houses was actually, or the tech challenge of insulating the existing housing stock, that's what it amounts to, was a big one. And I agree totally. Building new houses to high spec isn't really a problem. But, you know, housing stock turns over pretty slowly. Houses turn over with 50, 60, 70-year timescale. And the requirements have changed phenomenally in that time. And that would be a very useful technology developed, a really super insulating wallpaper that you could put on the inside of your house or maybe the outside of your house. We don't have it yet. Yes, please.
Sir, you're a physicist, is that not right?
I'm a geologist, really, but who dabbles in physics, yeah.
Well, I'm wondering about a perpetual motion machine based on uranium energy. Which is, I think it could be possible in the future because they've developed an encasing for uranium that's impenetrable. So then that means that it could be used in uranium like batteries that could be traded into commercial locations. Therefore, you know, I mean, we could come up with amazing innovations.
Well, I think anyone who invents a perpetual motion machine will have actually invented a money machine as well. But I think it's a little way away.
Well, I mean, you know, something to think about.
Mm-hmm. Yes, please.
What do you think about, well, you mentioned about dependency on the...
I can't quite hear. Can you speak up?
Yeah, you mentioned about dependency on the fossil fuel very quickly. Well, how about the, you know, when you mentioned about ice, how about the look at the diesel engine, you know, because then we can do the biodiesel, right?
Yeah.
You can grow biodiesel, then
Sure.
you just adjust your biodiesel, adjust your engine back to the Redox diesel.
Yeah.
Using a vegetable.
Sure. Yeah.
That way it's more efficient than the you know, like the gasoline engine.
Yes. The comment was that, yeah, we can, with biodiesel, we can move much more completely to diesel engines which are more efficient than gasoline engines, and that is quite right. Yeah. Sorry?
I just said they smell worse.
Yeah.
Why isn't carbon capture and storage the same as sweeping the dirt under the rug? I mean, are they going to eventually run out of places to store it?
Well, I've always myself done quite a lot of sweeping dirt under the rug, actually. Works pretty well, actually, if you're in a bachelor pad. I mean, I don't think that's a good argument, to be perfectly honest. I mean, what you're doing is actually putting that CO2 back ultimately where it came from. The Earth cycles CO2 from the atmosphere down into, it's actually trapped from the atmosphere by a range of geologic processes. It goes back into the interior Earth, up into the crust, out. CO2 is actually seeping out of the ground almost everywhere. I mean, the places that you really see CO2 in a sensible is in the carbonated springs. You know, if you buy Perrier, you're actually buying water, which has taken natural CO2 from the ground. It doesn't really bother me putting CO2 back underground. I mean, there's an awful lot of CO2 down there anyway. Actually, my rugs you oughtn't to look under.
I'm going to call this to a stop now. There is a pressing reason. There is a pressing reason, and that is an aeroplane leaving from the airport. And as you probably can gather, if you want 2 hours before departure, time is negative. I would like, on your behalf, to thank Lord Oxburgh both for coming to our department and being, well, what's a good way to say it? A real nice guy.